Imagine trying to comb a tennis ball covered in hair flat without creating a single swirl or cowlick. This seemingly simple task is topologically impossible. The Hairy Ball Theorem, formerly known as the Brouwer fixed point theorem for vector fields on spheres, dictates that any continuous tangent vector field on an even-dimensional sphere must have at least one point where the vector is zero. On the standard 2 sphere, S2, this means any attempt to define a wind pattern or a flow across the surface will inevitably result in a stationary point, a singularity. This zero point is mathematically unavoidable, representing a fundamental constraint imposed by the sphere's topology. This constraint is not about friction or material properties, it is purely geometric. A vector field assigns a vector to every point on a manifold. For the sphere, these vectors must lie in the tangent plane at that point, meaning they are tangent to the surface. The tangent space at a point P on S2 is a two-dimensional plane. A continuous vector field requires that small changes in position result in small changes in the assigned vector. If we attempt to define a non-vanishing vector field, every point must have a vector of non-zero magnitude. The theorem specifically addresses the impossibility of constructing such a field globally on S2 while maintaining continuity. This contrasts sharply with surfaces like the cylinder or the torus, where a uniform non-vanishing flow is easily defined.
The theorem guarantees the existence of a singularity, a point P where the vector field V of P equals the zero vector. This singularity is often visualized as a vortex, or a source or sink in fluid dynamics, or a cowlick in the hair analogy. The proof relies on algebraic topology, specifically homology theory, demonstrating that the existence of a non-vanishing field would contradict the sphere's non-zero Euler characteristic. If a continuous vector field V exists without zeros, we could normalize it to define a continuous map from S2 to itself, which is homotopic to the identity map. However, the identity map has degree 1, while a non-vanishing field implies a degree 0 map, leading to the contradiction. The crucial difference lies in the Euler characteristic, a topological invariant defined as the alternating sum of the number of vertices, edges, and faces of a polyhedral decomposition. The sphere S2 has an Euler characteristic of 2. The Hairy Ball Theorem applies specifically to surfaces with non-zero Euler characteristic, such as the sphere or the projective plane. In contrast, the torus T2 has an Euler characteristic of 0. Because the torus is topologically flat, it allows for a globally defined non-vanishing vector field, such as a constant flow wrapping around both major and minor axes. This distinction highlights how the global structure, quantified by the Euler characteristic, determines the possibility of smooth vector field definitions. To understand why the zero point must exist, we examine the index of a singularity. The index measures how the vector field rotates around an isolated zero point. If we trace a small loop around the singularity, the index is the net number of full rotations the vector field makes. For a simple vortex, the index is +1. For a saddle point, the index is -1. The Poincaré-Hopf Theorem connects these local properties to the global topology. It states that the sum of the indices of all isolated singularities of a vector field on a compact manifold equals the Euler characteristic of that manifold.
The Poincaré-Hopf theorem provides the formal mechanism proving the Hairy Ball theorem. Since the Euler characteristic of the two-sphere is 2, the sum of the indices of any vector field on S2 must equal 2. If the vector field had no zeros, the sum of indices would be 0, creating a contradiction since 0 does not equal 2. Therefore, at least one singularity must exist, or multiple singularities whose indices sum to 2, such as two simple vortices, or one complex singularity with index 2. This theorem generalizes the concept to any compact, orientable manifold, linking local behavior of vector fields directly to the manifold's global topological structure. The Hairy Ball theorem extends beyond the two-sphere. It applies to all even-dimensional spheres, Sn, where n is even. For example, the 4-sphere S4 and the 6-sphere S6 also cannot support a non-vanishing continuous tangent vector field. This is because the Euler characteristic of all even-dimensional spheres is 2. However, the theorem fails for odd-dimensional spheres, such as the 1-sphere S1, which is a circle, or the 3-sphere S3. Odd-dimensional spheres have an Euler characteristic of 0, allowing for the construction of a non-vanishing field. For S3, a non-vanishing field can be constructed using the Hopf vibration, demonstrating a smooth global flow without any zero points. In atmospheric science, the Hairy Ball Theorem implies that at any given moment, there must be at least one point on Earth where the horizontal wind velocity is exactly zero. This zero point is typically the center of a cyclone or an anticyclone, where the airflow is purely vertical or stagnant. While wind patterns are highly dynamic and non-stationary, the topological constraint holds instantaneously. This principle helps meteorologists understand global weather patterns, ensuring that models predicting atmospheric flow must account for these unavoidable singularities. The theorem confirms that a perfectly smooth global wind pattern without any calm centers is physically impossible on a planetary scale.
The theorem has practical implications in defining orientation and rotation. When attempting to define a continuous coordinate system or frame of reference across a spherical object, such as defining the up direction for a camera orbiting a planet, the theorem guarantees a singularity. This is known as the gimbal lock problem in a topological context. In robotics, defining a smooth, global rotation field for a spherical joint is impossible without encountering a point of ambiguity or zero rotation. Engineers must design systems that either tolerate these singularities or restrict the domain of operation to avoid them, often by using quaternions or local coordinate patches instead of a single global vector field. The Hairy Ball Theorem is a powerful example of topological rigidity. It shows that certain properties of a space, defined by its fundamental shape, impose strict limits on the types of continuous functions or fields that can exist upon it. This rigidity is independent of metric properties like curvature or size. It depends only on the connectivity and holes of the manifold. The theorem serves as a foundational result in differential topology, demonstrating the deep connection between the Euler characteristic, a simple counting invariant, and the complex behavior of vector fields. It confirms that the sphere is fundamentally different from surfaces that can be smoothly combed.